Now, while we're working with height, there are other variables that we can use here. You may have heard before of being able to apply this type of probability theory and normal curve to the discussion of IQ. We can apply it to this idea of IQ. We can apply it to the idea of weight. We can apply it to the idea of like daily caloric intake, or the number of steps that you take a day, or GPAs even, right? We could talk about this in the context of community college student GPAs. Not every variable can conform to this idea of the normal curve. The ones that will work within this class, however, will be applicable to this idea. But just know that not necessarily every single variable can conform to the normal curve. So that's just an important piece of information. Okay, let's go ahead and I'm going to remove this and let's move forward. We're now going to discuss z-scores. Z-scores can sometimes be referred to as standard scores. In the previous slide, when we were discussing the area under the normal curve, we learned that sigma represents standard deviation units. We are going to call the combination of a number with a sigma as a z-score. So a z-score, sometimes referred to as a standard score, measures how many standard deviations above or below the population mean a raw score is. That is to say that a z-score tells us how far from the mean a specific data point is in a normal distribution. In the normal distributions I've shown you up until this point, we have seen whole numbers as representative of certain markers along our normal curve. We saw 1 standard deviation below and above the mean, 2 standard deviations below and above the mean, 3 standard deviations below and above the mean. However, z-scores are what allows us to maneuver in between and beyond those particular whole numbers. Instead of only finding out what's happening at 3 standard deviations above the mean, we can instead learn what's happening at 2.5 standard deviations above the mean, or at 3.7 standard deviations below the mean. Okay, so z-scores allow us to kind of move between those whole numbers, and even the whole numbers themselves are actually representative of z-scores. But it's important to understand that we can find out what's happening at very specific points along this normal distribution. So while we often use z-scores of this symbol here, this plus sign with a minus sign underneath is read as plus or minus. You're going to see this a couple times throughout this conversation around probability and then samples and populations. So while we'll often use z-scores of plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations, z-scores can also represent data not found as standard deviations with a whole number, just what I was describing a moment ago. So z-scores allow us to compare results to a normally distributed population. This means that we can compare scores even when tests are not the same. Now I'm using the word tests very explicitly. I'm going to present an example in just a moment that uses the idea of tests. But it's not only applicable to talking about tests. Okay, we'll see that in just a moment. Here is our z-score formula. Z equals x minus mu divided by standard deviation. So these pieces of the notation represented here should be familiar. X represents a raw score, the mu represents the population mean, and the sigma represents standard deviation. So that is our z-score formula. You should definitely record this in your notes. So let's apply this idea of z-scores to an example. And like I mentioned, we're going to use exam scores. I'm going to read this prompt because, I put it together. So let's put this information to context and practice. I myself, as a professor of behavioral statistics, I'm constantly reevaluating and rewriting my exams. So this means that the exam that you've taken this semester, let's say exam 1, is not the exact same as exam 1 that students have taken in previous semesters. So since I'm constantly wanting to be sure I'm an effective professor, I can take the data from one semester's exam, convert it into z-scores, and then compare it to the performance of students from a previous exam. So even though they're not the exact same exams, I can still compare the scores to see how well students are performing. So let's say we take two students. Student A is, from, let's say they're from my fall 24 semester, and student B is from my fall 23 semester. So a whole year in between these students have taken these tests. We're going to take each of the scores that I'll provide the information to you in just a moment. We're going to convert them into z-scores and then compare how well the students did. So to make this comparison, we need three total pieces of information for each student. We need the individual scores, we need the average score of the exam, and we need the standard deviation from the exam. So for student A, we're going to say that their score was 86, the average score was 80, and the standard deviation was 3. For student B, we're going to say that their score was 81, the average score was 77, and the standard deviation was 2. Now, at face value, right, the raw scores themselves, a student performing at an 86 versus a student performing at an 81, we might want to jump to the conclusion and say, well, of course, obviously, student A did better. But again, if you keep in mind that the idea is that the exam student A took is not the exact same score or not the exact same exam student B took, then we can't make that direct comparison of only using their exam scores themselves. We need to convert them into z-scores. So using the z-score formula, we're going to calculate z-scores for each student and then compare them. And so here's our analysis. For student A, we plug in a z-score, the z-score formula, which remember is x minus mu divided by standard deviation. X is our raw score, and in this case, student A's individual score was 86, minus the average of 80, divided by the standard deviation of 3, and that equals positive 2. Now that positive 2 is really important. When you're calculating z-scores, make sure that you record what symbol is represented in your z-score. If you calculate a positive z-score and I ask you to tell me what that z-score is, I want you to include the positive symbol. If you calculate a negative z-score and I ask you what that z-score is, you need to make sure you include the minus symbol. For student B, calculating their z-score, remember that their raw score was 81, their class average was 77, and the class standard deviation was 2. Now in this case, for each student, we calculated a z-score of positive 2 for each student. So what does that mean, right? We're comparing positive 2 to a positive 2. So despite student A and student B having different raw scores, 86 and 81, they performed exactly the same in relation to their respective class distributions. Both of them are 2 standard deviations above their class averages. This shows that even though student A's raw score is 5 points higher than student B's, they achieved the same relative level of performance when we account for the different distributions of scores in their classes. So this is important for me to understand. Let's say I'm conducting this analysis and I'm comparing student scores from one semester to another. This tells me that my teaching is consistent, right? I'm consistently, teaching at a level that is allowing students to perform at 2 standard deviations above the mean, okay? If, for example, let's say student A ended up calculating to be a z-score of negative 2. If someone scored a negative 2, then they did worse than the student than student B. And not just because we're comparing their raw score, but by converting into z-scores, we are able to compare them against their class averages and then ultimately to one another, okay? So if the fall 23 student performed at a +2 and then fall 24 student performed at a -2, then I'm going to start asking questions about what it is that I'm doing, right? So this analysis is relevant to something. As one behavioral statistics professor, if I'm wanting to understand how well my students are doing or how poorly they may be doing in relation to another behavioral statistics class, I need to convert my students' data into z-scores, and I need to convert another class's student scores into z-scores in order to make that comparison. Because my class and my exams are going to look very different from the exams of one of my colleagues, and you can't just do a straight comparison of raw scores. All right. Oops. Hopefully this is all kind of clicking. So this comparison emphasizes how z-scores allow us to make fair comparisons across different distributions by standardizing measurements. All right.